Alright, in this video I'm going to be working some AP Calculus area volume free response questions. And this is homework 8.3. Okay, so this first one, I don't know what year it came from, but I recognize it. It's R being bounded by the graphs of F and H, where it looks like the cosine, this is going to be F right here, and H is going to be the downward facing parabola up above. Okay? So we're going to start by finding the area of R. So we're going to just integrate top minus bottom as x runs from 0 to 2. Okay, top is h. Minus f, well, that'll end up being plus 2 minus 3 of these cosines. Okay, and this is no calculator, so we should be able to do this one by hand. So I'm going to combine those. So it'll be 8, negative 2, x minus 1 squareds, and negative 3 cosine of pi over 2x's. Okay, I need to find an antiderivative. And then, okay, well, an antiderivative for negative cosine would be negative sine, but then I'm going to need to divide by pi over 2 to account for the chain rule. So it would be like multiplying by 2 divided by pi, so I've got negative 6 over pi sine of pi over 2x, as x runs from 0 to 2. Okay. So that would be 16. 2 minus 1 is 1, so 16 minus 2/3 minus 6 over pi times the sine of, plug in 2 for x, you get pi. Sine of pi is 0, so that would just be a 0. Minus, okay, when I plug in 0, I'll get 0 minus 2/3 of negative 1 to the third, so that would be plus 2/3. And then sine of 0 is also 0, so that would be another 0. And that's going to be a suitable area for our purposes, right? We don't need to do that in arithmetic. Okay, now part B is, this one's a little weird. You might not have seen one like this before, where they're going to say it's a cross-section area, but here's the formula for the area of the cross-section. 1 over x plus 3. And I think a lot of people look at this one and like, it can't be this easy, right? And what you're going to do, we know that it's going to be the integral from x equals 0 to x equals 2 of the area formula dx. And I mean, I don't know what kind of shape this is going to make. You know, it's going to always have area 1 over x plus 3, but it doesn't really matter. We're just going to integrate, be glad it wasn't more difficult. So here I'm going to anti-differentiate. Let x run from 0 to 2, so that would be the log of 5 minus the log of 3, which you could write as the log of 5/3, or you could not, right? That's good enough for free response. Okay. Part C is write, but do not evaluate an expression that gives the volume of the solid when R is rotated around the horizontal line y equals 6. Okay. Oh, and so I'm going to, just like normal, this one's going to be a washer volume. I'm going to set it up by sketching, labeling the sketch, and filling in the formula. So let's say that was h. That's y equals 6. And then we've got f down here. So that's f, that's h, and this is the line y equals 6. Okay, so that's going to be good enough. And so I'm going to start from the axis of rotation, and I'm going to reach the far edge of the region I'm rotating, and that will make my large radius. Top minus bottom, 6 minus f of x. Okay, then I'll get my small radius. Okay, that'd be b equaling top minus bottom. Top is y equals 6, bottom is y equals h of x. So that my volume that I'm going to write an expression for and not evaluate would be pi times the integral. X is still going from 0 to 2. Large radius squared minus small radius squared dx. Okay, and then that's us writing and not evaluating an integral. Okay, and then part D is saying write but do not evaluate an expression that gives the length of the graph of h between x equals 0 and x equals 2. Okay, this is probably the best part for us. We know our arc length formula, and that's all we're going to do. We're going to write it down. 0 to 2 square root of 1 plus the derivative squared, so that's h prime of x squared dx. Well, that's an integral expression that's going to work for our purposes. Okay, that was the first one. Okay, this next one requires the use of a calculator, and this region is bounded by the graphs of y equals log x, y equals 5 minus x, and the x-axis. First one is find the area. Okay, for me, I might find the area using an integral in y, just so that I only have to do one of them. So for 2a, I'm going to do that. Okay, now I am going to need to compute the intersection point here, so I'm going to bring out the calculator and do that. Y equals log of x and y equals 5 minus x. So we're going to graph this, and there's that intersection. We're going to calculate the intersect between blue and red. Give it a guess of, I don't know, 4. And I get x equals 3.69344414, and y is 1.3065586. Now, I recently learned that that means that we've got those numbers stored in x and y on the calculator, so I might just use that a little bit. Okay, so this is, we're going to be integrating right minus left. Over here I have y equals 5 minus x. If I solved for x, I would get x equals 5 minus y. Okay. Over here I have y equals log x. And if I solve for x, I'd have x equals e to the y. So my right minus left is going to be 5 minus y. Well, yeah, sure. Minus x equals e to the y. And then y is going to run from 0 up to this 1.3065586 number. Yeah. And we're going to integrate that with respect to y. Now, if I wanted to do that quickly without typing in all those decimals, I would integrate from 0 up to y. I'm just typing alpha and getting the y character. And I'm going to do, okay, 5 minus, we'll use x to stand in for y, minus e to the y dy. I'm going to get 2.986. Okay. In part B, we'll find the volume of the solid generated by rotating E around the y-axis. Okay, so just like always, I'm going to make a sketch, label the sketch, and then fill in the formula. So the y-axis is over here. My large radius is going to equal, on the right I've got x equals 5 minus y. And on the left I have x equals 0. And I'll get my small radius with, also with right minus left, x equals e to the y minus the y-axis, that's x equals 0. Okay, got my a and b. I'm going to say that the volume is going to be equal to pi times the integral from 0 up to that 1.3 number, 3065586, of 5 minus y squared minus e to the y squared dy. And so I'll type that in, pi times the integral from 0 up to y of 5 minus y squared minus e to the 2y dy. And I get 58.280. All right. Then part C, there is a value of k for which the horizontal line y equals k divides E into two regions of equal area. Write an equation gives the value of k. All right, so I'll draw this for us. All right, so there's this magic line that cuts it in half, right? And we'll call that y equals k. And what we're going to see is it's always the same right minus left that I was using to compute the area in part A. So I'm going to say, all right, if I integrate as y runs from 0 to k, right minus left was, I'll get my scrap of paper I just threw away, and right minus left was 5 minus y minus e to the y. And that's going to be equal to the top half where I'm integrating from k up to that special 1.3 number. 306.5586. And then that's an equation that would satisfy what they were saying, that the two areas are equal. You could say that this was half of the integral from 0 to that if you wanted, but you don't have to. All right, that was a good one. And, I did these first two. I did them both without a calculator, or I did them all the way through. Found the solutions. The first one I did without a calculator. The second one I used the calculator. I think the rest of the way, I'm just going to set these up and not evaluate them just because this is such a long problem set, and I'm hoping to finish this video in just one part. I'm going to be working on it all day and hoping to just get it done, but I think that'll help. All right, let R be the region enclosed by the graph of F and the horizontal line y equals 4. Okay. We are definitely going to need to use the calculator to find the value of that intersection, though, and I'm going to show you about something we can do when that happens. And you may have noticed I had to write that 1.30 whatever number a bunch of times in the last problem, and I don't want to have to do that a bunch. And so I'll just show you how can we avoid doing that. All right, so it's going to be x to the 4 minus 2.3x to the 3. Plus 4, I'm realizing that I can tell you that it's going to be at x equals 2.3. But, suppose you didn't see that coming, and you graph this. And you calculate the intersection between blue and red, give it a guess of, x equals 2.3, y equals 4. Okay, you can see that algebraically. If you'd set them equal to each other and canceled off the 4s, factored and solved, you'd end up with a 2.3. Okay, and looks like my calculator's out of battery. All right, so this is not a good example of one where we're going to say just, hey, let t equal 2.3 and just use t the rest of the way. We can write 2.3. We don't have a problem with that. Find the volume of the solid generated when r is rotated around y equals -2. Okay. Well, just like always, set up, sketch my region, draw the large radius. That's going to be 4 minus -2. 4 minus -2 is 6. small radius will be top is f of x, bottom is -2, so it'd be f of x plus 2. So the volume is going to be pi times the integral as x runs from 0 to 2.3 of a squared minus b squared. 36 minus f2 squared. And that's going to be the setup. Region R is the base of a solid. So I'm going to just try it again. Each cross-section perpendicular to the x-axis is an isosceles right triangle. Okay, so that's area is 1/2 base squared. Base is going to be top minus bottom. Top is y equals 4. Bottom is f of x. So then my volume is going to be the integral of 1/2 base squared dx as x runs again from 0 to 2.3. Here's another, split it into equal areas. You can see they're not that creative with the area volume free response questions. You know, like it's a very limited set of things they're going to ask you about. So, okay, just write it one more time. And x equals k, that's going to be a vertical line. So I bet it'd be, I don't know, right about there. Doesn't matter where it is. So we're going to say that the integral of top minus bottom up to k is going to be equal to the integral from k to 2.3, also same top minus bottom. So top minus bottom is 4 minus f of x. Bless you. Okay, and then we're going to find the perimeter of R. Okay, well, up here, this segment is going to have length 2.3, so it'll start with 2.3, plus we're going to have to run an integral to find the length of the curve. And that'll be x running from 0 to 2.3, formula being square root of 1 plus dy dx squared. Well, I could just write f prime of x squared dx. And since, you know, they already defined f of x for you in the statement of the problem, you're good to just type it in like that. I'm recommending that if you actually had to compute the perimeter, which maybe I'll borrow whose ever calculator was charging on the charger before me. And cool. So I'm going to integrate 2.3 plus the integral from 0 to 2.3 of the square root of 1 plus, and then I'm just going to take f prime of x myself, right? Rather than having, I don't know if any of y'all have tried to put math 8 inside of math 9. It does oftentimes work, but man, it takes a while. It's going to do a whole lot of arithmetic. And so I'm just going to take that derivative by hand, 4x to the third minus 6.9 x to the 2 plus 0. Okay, and then dy dx squared dx. And we get ourselves a perimeter 8, 9, 6, 7. All right, the next one. Let R be the region in the first quadrant. We've already done this one, I think. I don't know. I've done so many of these recently. This one feels really familiar, but maybe not. Maybe I did this one in class yesterday or something. Okay, so we're going to find the area of R. That shouldn't be too painful. We're just going to do y equals 6 minus y equals 2 root x. X runs from 0 to 6. So 6 minus 2 square root of x dx. Okay, and maybe I'll do this one. That's 2x to the 1/2. So antiderivative of x to the 1/2 is going to be 2/3 x to the 3/2. So this will be minus 4/3 x to the 3/2. No, not 6. That's going to be 9. Integrating in y too much. Right, so this depends on x right there, and this is going to want to be the ending x value, which is looking like 9 to me. And also, we'll be able to take 9 to the 3/2, which we wouldn't be able to do for 6. So that's going to be 54 minus 4/3 of 9 to the 3/2 is going to be 27. That's going to be 36. And then, that area would be 18 if we had to get it as an integer, but that's going to be fine for free response. Right, but do not evaluate an expression involving an integral expression that gives the volume of the solid generated when r is rotated around y equals 7. All right, and I did not leave room for the axis of rotation, so that's going to be y equals 7, this is y equals 6, and this is y equals 2 square roots of x. Large radius is going to be top minus bottom, 7 minus 2 root x. Small radius is this top minus bottom, 7 minus 6. Okay, so my volume is going to be pi times the integral as x runs from 0 to 9 of a squared minus b squared dx. And in part C, region R is the base of a solid. For each y between 0 and 6, the cross-section of the solid taken perpendicular to the y-axis is a rectangle whose height is 3 times the length of its base in region R. Okay, so what they're saying is, if this is the base here, height is equal to 3 times base. And then the area of a rectangle is base times height, which is going to be base times 3 bases, which is going to be 3 base squared. Okay. So I know my volume is the integral of the area formula, so it's going to be 3 times the base squared. And y is going to run from 0 up to 6. They kind of even told me that. But I'm just going to need to get base in terms of y. Okay. So if I have y equals 2 square root of x, that means that the square root of x is half of y. And x equals, if I square this, I'll have to square the half and square the y. It would be 1/2 y times 1/2 y, and then that would be 1/4 of y squared. I've got one for you up here. Where is it? Yeah, the big stack. Sorry, pardon me. All right. Now, I'm going to say, all right, I've got x equals 1/4 y squared. That's the y-axis. That's going to be x equals 0. So this base here is going to be right minus left. Okay. And, well, it's just going to be 1/4 y squared. And that's interesting. I'm not entirely sure why they wouldn't have you compute that, because that's doable. But, I guess there were other integrals on that test that you had to compute, and they were satisfied with what you did. All right. Okay. Let G be the region in the first quadrant bounded by the graphs of y equals square root x and y equals x divided by 3. Well, that was a calculator. Why not? All right, y equals square root x and y equals 3. No, that's not what it is. 1/3 x, so x divided by 3. It's going to intersect at x equals 9 and y equals 3. I guess if you got a calculator, you might as well just figure out where that happens, but yeah, 9 and 3. Okay, so finding the area of G, so like that, x equals 0, x equals 9, so I'm going to integrate from 0 to 9 on top minus bottom. Top is y equals square root x, bottom is x over 3. That's a job for the calculator. You're allowed to use it. I trust y'all to do that accurately. Find the volume of the solid generated when G is rotated around x equals -1. Okay, this one I might draw, a little more exaggerated. I don't know if that's to scale or whatever, but that'll work. And I'm going to need to work these equations around for x as a function of y. So that's x equals y squared, and this is x equals 3y. Large radius is going to be, on the right is the line, so that's x equals 3y. And on the left, I've got x equals -1. And so that'll be 3y plus 1. Then my small radius, on the right, I have x equals y squared, it's the curve, minus x equals -1, which is going to be y squared plus 1. Okay. So the volume is going to be pi times the integral of 3y plus 1 squared minus y squared plus 1 squared dy. And y is going to go from 0 up to 3. All right. Okay, now we're going to say region G is the base of a solid. Cross sections perpendicular to the y-axis are squares. We like the square ones. Okay, so that's going to be the base of my square. Area of a square is base squared. And I'm going to say, well, that base is going to be right minus left. On the right, I have the line. The line is x equals 3y. On the left is the curve, and that's x equals y squared. And then my volume is the integral of area. So that's take base and square it. And then we're going to let y run again from 0 to 3. Okay. And both of these are things that I trust you to run through the calculator accurately. Okay. Then find the perimeter of G. That's going to be troublesome. Okay, I'm going to say this is not the perimeter questions, the arc length questions with square root curves are troublesome because dy dx goes undefined kind of at the edge, and so we're just not going to do that. They would not ask you about that. I think I probably found this one and just added the perimeter question on and didn't really think about what that was going to entail. All right, so let R be the region bounded by the graphs of y equals sine of pi x and y equals x to the third minus 4x. Yeah, this is the one with the small pond, right? Yeah. That one's a little troublesome at times. Okay, the area of R. This is going to be... All right, this will probably be... This is the type of thing where if I was going to... Actually, I'll just copy them. They're not that complicated. I was going to say, like, let this be f of x and let that be g of x and then just use those, but I think we'll be fine. Area of R is going to be the integral from x equals 0 up to x equals 2, top minus bottom. This top thing, this is the sine curve, right? We know that. So top minus bottom. And this, we will need the parentheses for this one. Somebody was asking me earlier if the parentheses were necessary for this, and this one is definitely a case, because if we were to distribute that negative, then that negative 4x would become positive, and then it would be different from if I'd said minus x to the third minus 4x. Okay. And okay, that's something we could run through the calculator. The horizontal line y equals negative 2 splits the region R into two parts. Oh. So write but do not evaluate an integral expression for the area of the part of R that is below this horizontal line. So that's like if I just cut through right here and there. So I need to find those x coordinates, because that's going to be my region of integration. And so I'm going to need to type these into y equals. So this is the other one. This is x to the third minus 4x. And then I'm interested in where that runs into negative 2. Okay, so we're going to calculate the intersection between blue and red. It's going to be right there. All right. Now, this is going to be my lower bound of integration, and that's great. But we just solved an equation using the calculator. And on the free response section of the AP exam, if we solve an equation on the calculator, we need to report which equation we're solving and the solutions. So I'm going to say, all right, first things first, I need to find out where x to the third minus 4x is equal to negative 2. And that's going to be first at this x value, 0.5391889. 5391889, and also at a place that I'm going to have to find in a moment. Calculate the intersection, blue, red, guess over there. That's 1.6751309. Okay. So I've reported the equation I solved, I've reported the solutions, and now I'm going to say the part that's underneath is going to be the integral between these two x values, so 0.5391889 and 1.6751309. I suppose since the integral itself is your answer, you would probably be good to round those off to 3 decimal places without fear. But I'm just going to report all of them, just to be safe, right? And when I cut through that, I'm just going to have, it's going to look like that. So on top, I have y equals negative 2. And on bottom, I have x to the third minus 4x. And that's going to be the amount of area underneath that horizontal line that's still in the shaded region. Right. Now R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square by the volume. All right, I'm going to try to replicate this. That's the best I got. Okay. Cross-sections are perpendicular to the x-axis, and they're squares. I just did one like this, but it's fine. No, that's the base. Okay. Over here, I know area of a square is base squared. This base is top minus bottom, sine of pi x, minus x to the third minus 4x. Now the volume is the integral of base squared. And x is going to go from 0 to 2. Now, maybe I will do this one since I've got All right, I've got x to the third minus 4x and y1. I'll put sine of pi x and y2. And remember that we can just do integral from 0 to 2 of, I'm going to be squaring y2 minus y1. So I can call on y2, call on y1, square them, square their difference, I guess. Integrate, and that's going to get 9.978. Always 3 decimals. Now this one might be the hardest problem, just in terms of knowing what to do, because almost always they give you more direction, like rotate this around an axis, or cross sections are this. My interpretation of this is if the depth of the water is given by 3 minus x, then it doesn't matter how, vertically how far you are. The depth is always going to be the same, because it says at all points at distance x from the y-axis, the depth is 3 minus x. So say along this line here, it's a constant depth, meaning cross-sections are going to be rectangles, okay? And the height of the rectangle is going to be 3 minus x, and the width of the rectangle is going to be this distance right here. And if you didn't see that, I don't really know. I don't know how else to explain it. I have a feeling that whenever this was, on an AP calculus exam, this was probably the real thinker on the free response, or at least on the free response calculator section, that you really had to think about what it meant, and a lot of people were getting it wrong, and that's okay, right? It was the challenging problem. So what I'm going to do is I'm going to say it's going to be a rectangle situation. So really I'm going to use the same thing. That's going to be the base of my rectangle. Base equals sine of pi x minus x to the third minus 4x. And the height is going to equal 3 minus x. And we know that the area of a rectangle is base times height. So what I'm going to do is I'm going to say volume is equal to the integral of the area formula. Luckily, this depends on x, right? So I know x is going to run from 0 to 2. Base is going to be 3 minus x times and then we could type that into the calculator. It would be kind of annoying, but we could do it. Okay. And that was number 6. All right, halfway there now. Okay, now we've got y equals log x and y equals x minus 2. This is what I was trying to get to one like this. All right, so yeah. I'm going to graph these. So y equals log x and y equals x minus 2. I'm going to reset the window a little bit so that we can see this a little closer. Yeah. I think it's one of those things where if the calculator hasn't plotted it, it's not going to be able to find the intersection. It didn't look like it had plotted enough of y equals log x for me. So I'm going to calculate the intersection. Of course, we're going to need to blue, red, give it a guess. All right, that's one of them. Okay, if we're going to solve this equation, we're going to need to report the equation we solved. So that's log x equaling x minus 2. The second solution is equal to x equals 3.146, 1932. And the other intersection is going to be 0.1585. 1585943. Okay, and then I'm going to say, you know what? So that I don't have to keep writing these numbers repeatedly. Yeah, and oh, I should have definitely copied the, that's a shame, the y coordinates here, because I'm going to have to rotate around the y-axis later, so I am going to do that. That y coordinate is going to be negative 1.841406. I'll do this one more time. Guess is 3. And this is going to be positive 1.1461932. Oh, that makes a lot of sense because it's y equals x minus 2. Okay, whatever. It'll be okay. So what I'm going to do for this, since I'm going to have to write it twice and I don't want to have to keep writing that, I'm going to say let t equal 0.1585943 and u equal 3.1461932. And if I'm really explicit about defining those variables, I can just say, okay, the area of R is going to be the integral from t to u of top minus bottom, log x minus 2. That's another one where the parentheses are going to matter. Okay. And then that's something that we could run through the calculator. You can even store those two numbers in, you know, t and u on the calculator and do it that way if you wanted. Then we're going to find the volume of the solid when rotating this thing around y equals negative 3. So, and there's y equals negative 3. I'm going to draw my large radius, top minus bottom, y equals log x minus y equals negative 3. And then small radius is equal to top minus bottom, x minus 2 minus negative 3. So the volume is going to be pi times the integral from t to u of a squared minus b squared. So it would be log x plus 3 squared minus x plus 1 squared dx. We can run that through the calculator. And then lastly, we are going to write and not evaluate an integral expression that can be used to find the volume of the solid formed by rotating R around the y-axis. All right, this is y equals log x. This is x equals e to the y. And if this is y equals x minus 2, then I could add 2 to both sides, and x would equal y plus 2. Around the y-axis, there's a little bit of separation there. Okay, large radius is right minus left, y plus 2 minus... that y-axis is x equals 0. Small radius is e to the y minus 0. And so then I'm going to be integrating from this y value to that y value. And since I only got to do it once, I'm just going to copy the numbers, because you'd have to copy the numbers to say let y1 and y2 equal that. So we don't want to do that. Volume is pi times the integral from negative 1.841406 up to 1.1461932 of a squared minus b squared. So y plus 2 squared minus e to the y squared dy. All right. Well, that was a lot of problems for one sitting. I'm going to take a break and come back and do the rest of these in a few minutes. All right, I'm back. Let's keep going. So this one, R, S, and T r is bounded by e to the 2x minus x squared, and y equals 2. S is going to be parts of the curve, and y equals 1 and y equals 2, and then t is just everything below that, I think. Okay, so perimeter of t, that should be interesting. Anyway, all right, finding the area of R. That's going to require for me to solve for these intersection points. Okay, so I'm interested in where e to the 2x minus x squared equals y equals 2. So I need to find out where does e to the 2x minus x squared equal 2. And there's going to be 2x coordinates, and that will be what I integrate on to find the area. Now, calculator off the charger, and all right, so all right, e to the 2x minus x squared equals 2. I'm going to subtract 2, and I'm going to find where that equals 0. Okay, and then I'm going to set my window to 0 to 2, just so I'm not looking at anything I don't want to see. Okay, there's one of them, and there's another one. Okay, so I'm going to calculate the 0. The left bound would be 0, the right bound would be 1. Okay, x equals 0.446057003. Just copy that down real quick. Now, find the other intersection. I'll calculate a 0 between 1 and 2. I get 1.553943. Okay. So if I'm going to be integrating to find the area of R, I'm going to integrate from 0.446057003 to 1.553943 on top minus bottom. On top, I have this curve, which is going to be e to the 2x minus x squared. Minus on bottom, I have the line y equals 2. And that's going to be an integral that you could put into your calculator to get the right area. Okay, find the area of S. I was trying to see if there was going to be a faster way. Hold on a second. Let's see what I did last year. Turns out there was a finesse technique that I was not seeing. This is pretty slick. Okay, there's not really a much better way to do it besides breaking it up into 3 separate pieces, and we don't want to do that. So what we're going to do is we're going to solve for this intersection, and although it looks like x equals 2, it's not, right? Because we know that e to the 4 minus 4, e to the 0 is 1. Well, wait, is it? No, it is going to be 2, 1. Either way, I'm just going to make sure. Maybe, I mean, you might be watching me and be like, dude, that's completely obvious. You know, I want to find where this is equal to 1. Then I'm going to graph. I need to give myself a little more room, like maybe 2.5. Yeah, that's making sense that it would be at x equals 2. So, yeah, it's at 2. Okay, I get it. Okay, so what I'm going to do is I'm going to integrate from 0 to 2 to find the area of R plus S, and then I would subtract the area of R, right? So maybe I will actually compute that one. So math 9 from 0.446057003 to 1.553943 of e to the 2x minus x squared minus 2. I get 0.514. And then I'm going to integrate to get s. I'm going to integrate from x equals 0 to x equals 2 on top minus bottom. Top is the curve, bottom is the line y equals 1. So e to the 2x minus x squared minus, not 2, but 1. I was just mindlessly copying from above. That's what happens when you do that. And I'll do that, and then I will subtract the 0.514 to kind of cut off the r and just get the area of s. Because this integral right here represents the sum of the areas of r and s. All right. And then that's something that you could run through the calculator, and it wouldn't actually. Oh, whoops. Meant to just copy that. Minus 1. Minus, and I get 1.546. Right, but do not evaluate an integral expression that gives the volume of the solid generated when r is rotated around y equals 1. All right, so I'm going to draw r. I'm going to draw 1. I'm going to get my large radius and my small radius, just like always. Start at the axis, go to the far edge. Okay, large radius is top minus bottom, is e to the 2x minus x squared, minus bottom is y equals 1. Okay. My small radius, that's going to be 2 minus 1. All right, so now I'm going to say that the volume is equal to pi times the integral, again, okay, from 0.44605 to 1.5539, you know, that number, those numbers, a squared minus b squared dx. So that's going to be e to the 2x minus x squared minus 1 squared minus 1 squared dx. And that's me writing and not evaluating. Okay, find the perimeter of T. All right, well, I know that this has a length of 2 because I've investigated probably more than I needed to and found that that was, that intersection happened at 2. So I got 2 plus 3 is 5 and 1 is 6 plus an arc length that will give me that, you know, that thing right there. E to the 6, well, it doesn't actually connect. That's troublesome. Hold on, let me make sure that that doesn't actually connect. Make sure I'm not missing something. Y equals e to the 2x minus x squared. And we'll go all the way to 4. All right, I'm going to calculate the value. I don't really use calculate value very often, but I'm going to plug in x equals 3, and y is very small. So maybe I'll assume that there's a little small vertical line there, you know? Very small, right? 0.0497. So it's going to be 6, you can see that, 6 plus 0.049787 should be, that's enough. Plus the integral from 2 to 3 of the square root of 1 plus dy dx, okay, the derivative of e to the 2x minus x squared, is going to be e to the 2x minus x squared multiplied by the derivative of the exponent, would be 2 minus 2x. 1 plus dy dx squared dx. We could run that through a calculator, right? And get ourselves a perimeter. I'm not going to do that right here. Okay, that wasn't a real question, especially, you can tell because of that little issue over there with that 0.049. All right, so that's, well, I don't know where my last page is. Under here. All right, number 9. Starting to get closer. Let f be e to the x and g be log x. enclosed by the graphs of f and g between 1/2 and 1. Let's just remind ourselves what we're looking at. E to the x, that's f of x, and g of x is log x. Yeah, we'll zoom standard. Okay, that's a little weird because it's not really enclosing anything, but okay, what I'm saying is, what I assume is, okay, here we've got e to the x, and here we've got log x, and we'll say 1/2 to 1. Okay. That's the area that we're trying to find, okay, or at least I'm assuming. So it's the integral from 1/2 up to 1 of top minus bottom. And we could run that on the calculator. Find the volume of the solid when that region is rotated around the line y equals 4. Okay. Yep. So large radius is going to be top is 4, bottom is log x. Small radius, top is 4, bottom is e to the x. The volume is going to be pi times the integral as x runs from 1/2 to 1 of large radius squared minus small radius squared. So that's going to be 4 minus log x squared minus 4 minus e to the x squared dx. And you could do that on the calculator. Let h equal f minus g. Find the absolute minimum value of h on the closed interval 1/2 to 1. Cool. All right, well, we're going to find h of 1/2, h of 1, and, all right, so first of all, I'm interested in, I might actually call this one y1 minus y2. And then I'm going to plug in to y3. I'm going to plug in 1/2, and I'm going to plug in 1. Okay, so I've got these, and I'm just going to kind of relate those to you. 2.342 and 2.718. All right. Yeah, and then I'm going to also need to consider, in addition to the endpoints, the critical points, the places where h prime of x, which is equal to f prime of x minus g prime of x. And we know how to take this derivative, right? If f is e to the x, f prime is e to the x. And if g is log of x, g prime is 1 over x. And we're interested in where that equals 0. So I'm going to do a little investigation and find out where that is. Okay, so I'm just going to not graph any of these things, and I'm going to instead now graph e to the x minus 1 over x. All right, and I'm graphing that on the interval 1/2 to 1 so that I'm only looking at zeros of the derivative that I'm interested in. Okay, there it is. I found one. It's also a relative minimum, so I feel like my chances are good for that to be the absolute minimum. But we're going to calculate the 0. The left bound is going to be 0.5. Right bound could be 0.7. And the 0 is going to be, I thought maybe because it was pink it wouldn't show up that well, x equals 0.5671439. Okay. And then I'm going to evaluate h at that point. So I'm going to plug in on y3 with that critical point, which is 0.5671439, and I'm going to get 2.330. And there it is. That's the absolute minimum. We're happy. All right, now we're going to let f be the function f equals e to the 1/2 x, y equals 3, f, and the y-axis. Okay, we can do that. Okay, y-axis, y equals 3, e to the x over 2. Okay, and so I'm going to integrate top minus bottom to find the area. So I'm going to be integrating top is y equals 3 minus bottom is e to the x over 2 as x runs from 0, which is the y-axis, all the way up to this intersection point. Now I'm going to have to solve for that intersection point, so I might do that kind of off to the side. Use a different color. And I'll say e to the x divided by 2 is equal to 3. So if I want to get at that x, I'm going to have to take the log of both sides. So the log of e to the x over 2 is going to be, just x over 2, or maybe I'll call that 1/2 x, equals the log of 3. And then x is going to be 2 times the log of 3. Okay, and that'll be my upper bound of integration. Okay, now 2 log of 3, that is the same as log of 9, but we don't need to do that. And then that's going to be an integral that would give me that. Just the only thing to worry about is here when taking that antiderivative, just make sure that you're getting 2 e to the x divided by 2 to account for the chain rule. Okay, but finding the volume of the solid generated by rotating r around the x-axis, okay, same thing. Draw the sketch, label the sketch. And we're going to label our sketch some more. Top minus bottom, 3 minus 0. Small radius is e to the x divided by 2 minus 0. And then the volume is going to be pi times the integral as x runs from 0 to 2 times the natural log of 3, like I just learned above right here, of a squared minus b squared. That's pretty nice, I gotta say. If we had to do this one by hand, if I had to pick one to do by hand, it would be that one, right? Okay. So when I square e to the x divided by 2, e to the x divided by 2 squared is what we multiply the exponent, so it ends up just being e to the regular x. Well, we can do that. All right, then find the volume of the solid generated by rotating r around the y-axis. That's going to require a calculator because of the natural log. Okay, so and then that's the y-axis right here. Whoops, this got worse and worse. Anyway, that's going to be x equals 0. So I'm going to need x equals right here. And we kind of already back solved that once, so it's gonna go very similarly. If we're interested in y equals e to the x divided by 2, x divided by 2 will be log of y, and x will equal 2 log. Okay. Right, and then this is y equals 3. Now I'd say it's probably worth pointing out that this intersection happens at y equals 1, because I'm going to need to integrate from y equals 1 up to y equals 3. All right, so this volume is going to be pi times the integral from y equals 1 to y equals 3 of, this is a disk scenario, so I just have one radius, and it's right 2 log y minus left is x equals 0, and we're going to square that and integrate with respect to y. Okay. One more page, 2 more free response problems. Almost done with this. It's, okay, yeah, already over an hour. No surprise there. I will say, though, if this is truly, in fact, 12 free response problems, remember that in AP Calculus, for a free response problem, we're budgeting 15 minutes per question. So this would be 3 hours worth of problems. And that's why I was telling y'all, I was begging you to please not do all these in one sitting, and I really am hoping that nobody is just watching this having already run through an hour of this. That would be too much, right? At a certain point, too much practice is too much. it's not as bad as not enough practice. So I'll always make the mistake of giving you too many practice problems over not enough. I would never do that. So let N be the region bounded by the curves F and G. Give a sketch of N. All right, 4 over X is going to kind of come down like that. All right, so I'm just going to really approximately sketch that. And then there's going to be a parabola. All right. I don't know where this problem came from. I don't know if this is an actual one. I don't think they wouldn't ask you to anymore. There are some old AP calculus problems that ask for a sketch of a region or of a polar curve or of a parametric curve, but we don't do that anymore. So let's do 4 over X and X minus 3 to the 2 power. Nope. I'm interested in the standard window. Oh. Let's see, they look kind of like they were sitting tangent to one another, and it definitely does look like they are. So, okay. How are you supposed to know that without a calculator? But it doesn't look like a parabola at all, but you can just suppose it was. All right, that's the sketch. Find the area of N. Okay, well, we're going to need to compute the intersections, and maybe I'll do that by hand. Okay, so I feel like that might require some algebra here. So 4 over X equals X minus 3 squared. I'm going to actually square it. So I've got X squared minus 6X plus 9. And then I'm going to multiply both sides by X, and so I'll have 4 equaling X to the 3rd minus 6X to the 2 plus 9X. And this is not factorable. But X equals 1 does work. Okay, so I'm just going to call on X equals 1. 1 minus 6 is negative 5. Negative 5 plus 9 is 4. 4 minus 4 is 0. Okay, so X equals 1 works. And then the other intersection point, what is the other one? It's probably 4. Right? 4 divided by 4 is 1. 4 minus 3 squared is also going to be 1. Okay, yeah. X equals 1, X equals 4. Okay, so I'm going to integrate from 1 to 4, top minus bottom. On top was this kind of decaying curve, so it was 4 over X. Minus bottom is X minus 3 squared. And that's an integral for the area. And you could compute that by hand. You could compute it with a calculator, however you want. Find the volume of the solid generated by rotating N around the x-axis. Okay, so I'm going to that's a better sketch. Around the x-axis is going to be right like that. Okay, large radius is going to be top minus bottom. My small radius is going to be top minus bottom. So the volume will be pi times the integral from 1 to 4 of large radius squared minus small radius squared. All right, last one. A is bounded by the graph of x squared and 4. Find the area of A. Okay, well, that's going from -2 to 2. Maybe I'll say that that's going to equal twice the integral from 0 to 2 of top is 4, bottom is x squared. And find the volume of the solid generated by rotating A around the x-axis. All right, well, my large radius is going to be top minus bottom. It's going to be 4 minus 0 is 4. And my small radius is going to be top minus bottom would be just x squared. Okay? So the volume is going to be pi times the integral from -2 to 2 of large radius squared minus small radius squared. And you could do that by hand. Oh, but we need that for the next part, so I'll show you how to do it. I might need more room than I've provided those. So I'm going to go over here, add a post-it note, and say, all right, this is pi times 16x minus 1/5 x to the 5th, x running from -2 to 2. And so that's going to be pi times, plug it in, get 32 minus 1/5 of 32 minus, and then over here when I plug in -2, I'll get -32 here, but then I would end up plus 1/5 of -32, or minus 1/5 of -32 would be plus 32 over 5. Which, if we had to combine them, would be pi times, all right, well, that'd be 4/5 of 32. And then I'm just going to add another one. So that'd be 8/5 of 32. Pretty sure that's what that's going to be. 8/5 of 32. Yeah, 256 over 5, yeah. And all right, so I've got that. We computed the area. I can use this number to, there's a number k bigger than 4 that when we rotate around that, we get the same volume. So volume, I know, is going to need to equal 256 pi divided by 5. That's the volume. Is going to be pi times the integral from -2 to 2, and I think I'm going to put my sketch up here. Okay, that's y equals k, and then that's the same thing. So my large radius right here is going to be k minus x squared, top minus bottom. And I'm kind of running out of room here, so I'm just going to kind of do this all at once. My small radius is going to be k minus 4, top minus bottom. K minus 4 squared dx. Okay, and that's the volume integral. That's what the result is supposed to be. Okay. And then find the perimeter of A. All right. Well, this goes from, you can't see that, but this goes from -2 to 2, so that's going to have a width of 4. That straight line will have a length 4, plus the integral from -2 to 2 of the square root of 1 plus dy dx squared. And then that's something you would use a calculator for. Oh, did not realize that this allowed for the use of a calculator. That I could have done this using technology and I wouldn't have had to do that. But, you know, always good to do a little bit of by hand integration. All right, that's it for homework 8.3. That was a lot of AP Calculus area volume free response questions. But, you know, if you felt like you needed the practice and you did all of these, I'm telling you, you got the practice you needed. Okay, thanks for watching.